Okay, mentioned in the notes that one thing that makes this function special, in fact we already talked about the derivative formula, is that the function e to the x is its own derivative. So not many functions have that property. In fact, the only one I can think of is the zero function. If you remember the rules of derivatives, the derivative of a constant is zero. So this function also is equal to its own derivative, but it's not a very interesting function. E to the x, though, is a function with a really interesting graph, and basically when we make this statement that the function is equal to its own derivative, it kind of tells us something that you can notice on the graph. For instance, right here, well, when x is 1, let's say, okay, well, when x is 1, the y value is e to the power 1, which is e, or about 2.718. So not only is that the y value here, that's actually also the slope of the graph. This tangent line at that point, when x is 1, has a slope of 2.718. And if you go over here to, for instance, -1, okay, at this point, well, that's the point, -1 comma e to the power -1, which is something like, what is it? It's about say 0.37, okay. Well, that's also the slope of the tangent line to the graph right here. So the slope of this tangent line is about 0.37. So that's a statement that's true anywhere on the graph. The y value happens to be also the slope of the graph at that point. And one thing that we'll see again, especially in some upcoming sections, is that functions that look like e to the x, general exponential functions, grow in a way that is kind of dependent on their own size. So the bigger an exponential function gets, the faster they grow, right? The slope is really the growth rate of a function. It's how quickly it's moving upward. So when an exponential function gets bigger, it actually is growing faster, and when they're small, they tend to be growing slower. So anyway, I just wanted to illustrate that a little bit.